Hello and welcome to a new episode in my Homebrew Spectrum Analyzer series. Today I want to test that guy here, which is the 10.7 MHz DDS module. As you can see, I've already soldered up everything. It's ready for use, but I haven't powered it up yet, so you'll be able to witness whether it works properly or not. Now, to freshen up your memory, the DDS module is in the block diagram. The big picture of the spectrum analyzer is that guy here. Essentially, an input signal entering the instrument first enters that first mixer where its output is filtered at around 1 GHz, then down converted to 10.7 MHz, filtered, amplified, filtered a little bit more. Essentially, the power is measured using the log detector and the result is digitized by the ADC. These two modules here, I've discussed them already in previous videos and I'm going to use them in today's experiment. So basically, the DDS is the reference to the phase-locked oscillator that drives the first mixer of the instrument, and that is also responsible for doing all the sweeping of the instrument. The schematic of the DDS is as follows. I've already showed this in previous videos. Basically, there is 3 blocks. The first block is the DDS chip itself. Now, I have discussed this extensively. I went to the length of actually hacking up a crude, discrete DDS to show how it works and all that. The output of the DDS, though, it's at 10.7 MHz, sine wave in theory, but it's not very clean. It's got lots of undesired frequency components, and we're going to look at that. So during the experiment, I'm going to measure the output of that guy directly, and hopefully we'll see a 10.7 MHz that is not very clean. Now, this is why there is a monolithic crystal, 10.7 MHz crystal over here to filter out the undesired frequency components and hopefully to end up with a sine wave of 10.7 MHz that is reasonably clean. That sine wave is squared up by the squaring circuit, and finally we get a 10.7 MHz square wave. That's sort of the final product of this guy. Now, if we look at the connectors, there is one input here, clock in, which is the reference input of the DDS. The 3 other connectors are outputs. The square out is the final output. So here, if we measure here, we should get a square wave. And then there is 2 DDS outs, DDS A and DDS B. In the schematic, that's this guy and that guy. Now, DDS B just gives you an auxiliary, you get the output of the DDS twice. You get it once into the path that I just discussed, and you get it a second time, and there's just this connector here. So if I hook up something, the scope to that connector here, I'll see the output of the DDS directly. The other DDS output, this is sort of an either-or thing. Either you decide that you want another output, then you populate the connector and that capacitor here, but you do not populate this inductor. So basically you have this DDS output twice then. Or you do not populate the capacitor and the connector, but you populate the whole path, and basically you get it once unfiltered and once filtered via this monolithic crystal filter, which is what I have done. I have populated the connector just because it looks nice, but I haven't populated the capacitor. So basically that output here doesn't work, it just looks nice. In any case, this is probably a good time to mention that I have another video about DDS that is not part of the Spectrum Analyzer series, where I explain a little bit what kind of frequency components you get out of a DDS. It's not very, there isn't a lot of mathematics. I actually wanted to put a little more math. If you want to see that, put it in the comments, but basically that video just explains a little bit what you can expect from a DDS and essentially why you have to filter the output, which is what we're doing. If we look at the module, that guy here is the monolithic crystal filter that is responsible for the filtering. And finally, that is the suggested experiment for testing the DDS module. Here is the DDS module. You can see those blocks, the DDS, the crystal filter, and the squaring circuit. And this is then supposed to be fed into a logarithmic detector the module that I already have. It's essentially going to measure the power and digitize it by the ADC. So let me set up everything, get ready, and then we'll take a few DC measurements and then a few AC measurements and look at the output of this test. Okay, so while I was setting up everything, I realized that I have a bit of a problem, because this test, as you can see, requires the 64 MHz master oscillator module. That's just a module with a 64 MHz oscillator that fans out that 64 MHz reference square wave 2-3 SMA connectors. But unfortunately, I don't have that module yet. I have already designed the PCB and it's in the fab as we speak, but I don't have it yet. So that's a bit of a problem, because without reference to the DDS, you know, this test is not going to be very fun. So what I'm going to do instead is I'll use this guy here, which is a Etherkit Si5351A Breakout Board. What that means is that chip on that board here is a PLL clock distribution chip. This PLL chip can generate all sorts of frequencies that are derived from this local oscillator here. In that case, you know, 3 connectors, it can generate 3 signals, and I'll just use that to generate the 64 MHz signal. Now, I got this because I want to check it out for other projects. This breakout board is about 10 euros, and I highly recommend it. It's super cool, you know, very easy. They provide you with an Arduino library to set it up, and it's really easy to use. I am going for the easy way out here, and I just use that along with the provided Arduino library and the spare Arduino I have for the experiment. Now, this is also interesting because in theory this can generate a 10.7 MHz signal on its own. In fact, it can generate several signals that are synchronized with each other. So it's worth thinking about whether you can use this as 10.7 MHz generator itself, because to be honest, the DDS is sort of a convoluted way to do that. Now, I'm not sure, I haven't thought about this, it's not for today anyway, because the DDS has a phase noise that is comparable to the reference input of the DDS, while a PLL sort of amplifies the phase noise of a reference. So I haven't thought about this. Maybe, you know, you can't do it for that or for another reason, but anyway, this is not for today. I'm just going to use this for a 64 MHz reference and run the test otherwise as shown here. The first thing I want to do is check what kind of signal I get out of this Etherkit breakout board. The reason for that is I haven't worked with it before, and I haven't worked with the Arduino library either, so I just want to make sure that that 64 MHz reference is fine there. In order to do that, I connected the breakout board to an Arduino Nano. I've got a 5-volt supply, a ground return, as well as an I2C line here with the yellow and the green cable. This then goes to an SMA to BNC connector, and the whole thing is hooked up to my oscilloscope, which you can see here. Now let me focus on the screen. Right, and I've wrote a very simple program for the Arduino Nano. It's actually the example that comes with this Etherkit thing, just with a frequency change, and I'll just program that into the Nano and see what I get. This will take a few seconds, and in fact, by the way, when you order this Etherkit thing, they sell you the connectors, those SMA board edge connectors. They sell them, so all you have to do is just solder on these connectors. Nice, so that doesn't look all too bad. Let me set up the scope in order to see that signal a little bit better. First, let's zoom in on the vertical, zoom in on the horizontal, and actually trigger, right. And let's terminate the scope into 50 ohms and readjust the trigger, zoom in a little bit more. Right, so that's not too bad. A couple of comments on that. First of all, this isn't exactly a sine wave, but it's also not a nice square wave either. And the reason for that, one of the reasons for that is my scope is actually bandwidth limited to 100 megahertz. So this being a 64 megahertz signal, the third harmonic will be somewhere around 180 megahertz. So it will be attenuated quite a bit by the scope itself, which is why the signal that is displayed is a little bit distorted. So this is something to be aware of. Other than that, I can see that I've got pretty much 64 megahertz. I could calibrate that out, but I don't really care about that. And also I have 1.6 volts peak to peak. And I hope that this is good enough, because in fact the DDS board is probably going to work best with a waveform that has a higher amplitude. But if we look at the schematic, actually, let's turn that down again. If we look at the input section on the schematic here, this is biased at half the rail and terminated into 50 ohms. So this being biased at 2.5 volts is probably going to be good enough for me to get away with sending in such a signal that is so low in amplitude. Anyway, so this is fine. So I'll extend the setup a little bit, put in the DDS module, and go from there. Okay, so I think I'm almost ready. I've taped everything to the bench, but it looks very messy, although I think it doesn't get any better. So let's see what I have. Let's start down here. This is the Arduino and the Etherkit Breakout Board that is connected to my laptop and is used to control and power the Etherkit Breakout Board in order to generate that 64 megahertz reference clock. That 64 megahertz reference clock makes it into the DDS board, where a 10.7 megahertz square wave is synthesized. That's the whole point of this board. Now, I will then connect the output of that board to the logarithmic detector over here using this cable. I haven't done that because there is a little caveat there and I want to make a few DC measurements first. But in the end, once I have this guy connected to that guy, and that guy is already connected to the ADC, essentially I will be able to measure the output power of my DDS board. So that's sort of the final goal, to be able to measure the output power of that guy. But before that, I want to take a few DC measurements. Now, one thing I want to measure is the 10 volts input, because this guy over here, that's the control board. The control board connects to the computer using this ribbon cable, and the computer is running the spectrum analyzer software where I can set up a few things. And in the end, this guy is going to both power and control the remaining boards of the project. And the voltage that it's generating using this 10 volts regulator, well, is 10 volts. So basically we have 10 volts in here, a 10 ohm series resistor to do a bit of power supply noise rejection, these kinds of things, and then a local 5 volts regulator. Now, if I measure the 10 volts here and the input voltage here, I could calculate the voltage drop across that 10 ohms resistor and figure out how much current this is drawing, because according to the documentation, this should pull 62 milliamps when idle. I find that's a bit low, but we'll see. So I will measure those 10 volts here, the input to the local regulator, the output, which should be 5 volts. And in theory, I should measure, every pin that is connected to the rail, but I think I'll just measure a few decoupling capacitors, because to be honest, there is no way for me to probe that from the side with a camera in the way. And finally, I'm also going to probe the input to the squaring circuit, because this circuit here is... So if you look at the output, there is this feedback resistor here that makes it back to the input, and that is in order to self-bias the input. So because this is powered with 5 volts, in the end the input should sit at half rail at 2.5 volts. That's because when this is an inverter, so when the output exceeds 2.5 volts, the inverter is going to try to invert that, and if the feedback is done right, then it's going to settle on 2.5 volts at half rail, which is what I want to check. Great. So first I will power this on. I haven't done that before, so let's hope everything goes well. We should see a lot of blue LEDs going on and hopefully no smoke. So that looks fine. Few blue LEDs went on and it's pulling 50 milliamps. Okay, so I'll zoom into the DDS board to discuss that board a little bit further. It's pretty much just like you've seen in the schematic. The reference clock gets in here. That's the 5-volt regulator here. This is where the reference clock gets in. That's the DDS chip, and then that's the auxiliary output that I talked about before, and the actual signal that I want to clean up and deliver to the output of the board then turns around to the other half of that board that is nicely separated using this fence. That's the crystal monolithic crystal filter that is supposed to clean up the waveform, and finally the squaring circuit is up here, and there is an SMA connector to tap off that signal and feed it to the logarithmic detector or the phase-locked oscillator. So first off, I'm going to try and measure the 10 volts at the input, which is not working because I should probably connect a ground lead. Sorry for that. Okay, so that should be 10 volts, which it is, very nice. And the input of the regulator is 9.8, 9.9. So this is pulling, because it's across 10 ohms, this is pulling somewhere between 10 and 20 milliamps, which is not enough. Although I'm wondering what will happen when I turn on the software that is responsible for doing the sweeping. So we're at 9.8 and the software is starting, and it dropped to 9.7. So this is pulling now an extra, let's say, 10 milliamps, and in total we're at about 30 milliamps or so, which is still not the 60 that we should have, but it's already closer. Now, one more thing I should do is turn on the 64 megahertz reference clock. I do that by programming the Arduino, which is happening as we speak, and hopefully this will drop a little bit more. Come on. It's still programming. Okay, now it dropped to 9.3. So this is pulling roughly 70 milliamps, which is ballpark the right amount. So that is great. Now the output of the regulator, the output of the regulator is 5 volts. That's nice. And as I said, I just probe a few of those decoupling caps to make sure that we've got the correct. Okay, that's ground. So these were, all three were 5 volts, so that seems to be fine indeed. I can also try and probe the input to the squaring circuit, the power to the squaring circuit, which is 5 volts as well, and the input to the squaring circuit should be 2.5. Okay, so everything looks just fine. Next, we'll have a look at a few waveforms. The first waveform I want to look at is the unfiltered output of the DDS. I'll hook a probe to that auxiliary output of the DDS. The probe is not terminated into 50 ohms, so I'm really crudely probing this. Knock down the trigger and increase the horizontal time base. Now, okay, so that's not what I expected. What I see here is two things. The first one is there is this waveform here that looks sort of jagged. Now that is what I expected, but the strange thing is what's going on in the background. There is something that sort of kind of zooms in and then zooms out. I hope you can see that on camera, and I'm not quite sure what that is. I don't think it should be there. However, the spectrum analyzer software is still sweeping. So this might be an artifact. Maybe it's doing something strange when it hits the end of the sweep. I'm actually not quite sure what it's doing. When it hits the end of the sweep, I guess it turns off everything, waits a little bit, and then starts with the next sweep. I'm not sure, but what is for sure is that regardless of the sweeping, the DDS module should always output 10.7 megahertz, because the sweeping itself is done by the PLO, by the phase locked oscillator, and the 10.7 megahertz is just a reference to that. So what I will do is I will switch the software. Oh, now it okay, so it's sweeping. Now if I open a menu, it goes away. Okay, fair enough. What I can do is I can set a special mode where I can control the DDS independently of the sweeping, and I can set this to 10.7 megahertz, and that looks much better. So basically what you can see here is the unfiltered output of the DDS, and if I single shot that, you can see that this is really a very ugly waveform. Now the reason that you can see these steps is the master oscillator is 64 megahertz, and we're outputting a 10.7 megahertz signal, which if you divide 64 by 10.7, you end up with something that is sort of very close to 6, but not exactly. It's a bit lower. So essentially you should have 6 discrete steps here, and then once the accumulator overflows, it will every single time it will overflow to a slightly different number, which is why you're not sort of getting always the same waveform. So that's exactly what it should be. Excellent. Next, if I probe the output of the filter, which is that guy, oh, that is very nice. So that is a nice filtered output, measured 10.7 megahertz exactly, and 1.3 volts peak to peak. And lastly, I'm going to measure the output of the squaring circuit. That should be, in theory, a 10.7 megahertz square wave. Now, if I measure that, actually that signal is much larger, should be 5 volts peak to peak, which it is, but look at that, a very ugly signal. Now, that is due to the nature of how I am probing this, and I was sort of expecting that. Again, because this is a square wave, we have very fast edges in there that translate to high frequency components, and now transmission line effects are sort of starting to distort our signal. So what I will do is I will take so channel 1 is what I was using so far. Now if I turn off channel 1, turn on channel 3, which is connected to a BNC cable, and if I take that SMA to BNC adapter and hook it to the output of the squaring circuit. So basically now I want to take a proper measurement with a 50 ohms terminated scope through that coaxial cable, and I could already see this change quite dramatically. Okay, now I have to change the trigger obviously to channel 3, and yes, so that is excellent, very nice. I can add a measurement if I want to measure the frequency of that on channel 3. Obviously this is 10.7 megahertz again, so excellent. So that is exactly what I expected and what I was hoping to see, and I'm quite happy with that, and I'll proceed to the very last experiment. Since this video is almost 30 minutes already, I think I'll split off the final power measurement into a second part, because that's easily going to take me some extra 10 minutes. But before I go, I wanted to show you what I have running on my PC, which is the spectrum analyzer software just running. So that's basically the thing that you get when you fire it up. And when I opened up a menu, this is when it stopped, curiously. So now it's not sweeping anymore, and what I did to command the DDS to the fixed 10.7 megahertz was using this special test window thing, and then I can enter a frequency here, the frequency of the reference clock, which is 64 megahertz, and set it to the frequency that I entered. Okay, I hope that was interesting. I hope I see you again for part 2 of this video, and I say thank you for watching.